Hi there. In this lecture, we're going to see some very interesting and cool properties of networks or graphs as you have seen them. So before we get started, a few definitions again. What is a network or a graph? A network or a graph are synonyms, by the way. So a network or a graph has vertices or nodes. For instance, in the Facebook graph, each user is a vertex. In the internet graph, each router or switch is a vertex. There are edges that connect pairs of vertices. In the Facebook graph, a friend relationship between you and one of your friends is an edge. Similarly, in the internet graph, the link joining two switches in the internet constitute an edge in that graph. So there are networks or graphs all around us. The internet, of course, is one of the largest networks that we use. The World Wide Web is a network where the vertices are web pages and the edges joining them are links that point from one web page to another. This is often called a directed graph as the edges are unidirectional. There are also social networks such as Facebook, Twitter, and LinkedIn, which are all networks where the users are vertices and the friend relationships or the connections are edges. And of course, there are biological graphs such as DNA interaction graphs, ecosystem graphs, and of course, all of these are networks as well. So there's a variety of networks, and all these networks are fairly complex. They have different kinds of complexity. The first kind of complexity is structural complexity. For instance, the human social network has about 7 billion nodes. That's the number of people alive in the world as of this year, 2014. There are millions of computers on the internet. The graphs or the networks as a result of these large numbers of vertices are also structurally very, very complex. These networks evolve over time. They don't look the same now as they did 1 year ago, and they don't look the same now as they will 1 year from now. This is because people make friends all the time, new people are born, people die, relationships change over time. In the internet, the ISPs change hands all the time, so the links in the internet change as well. And of course, in the World Wide Web, as you know, the new pages are created as well as new edges and new links are added all the time. And there's a lot of diversity even inside any one of these graphs. Inside the human social network, for instance, some folks are more popular than others, so they might have more friends than others. In the World Wide Web, some websites may have many more links than others. They have many more links pointing to them than other websites do. For instance, the BBC website has many more links pointing to it than your or my personal homepage does, likely. And of course, the vertices in these networks are fairly complex. In the internet graph, the endpoints, the routers or switches have different kinds of CPUs. They're running different kinds of OSs. And these OSs themselves have a lot of complexity. And of course, human beings in the human social network are very complex individuals as well. And even though you might be able to represent each of these vertices by a few simple rules, when you put a large number of these vertices together in a network, you get some very complex global behaviors. These are often called as emergent phenomena. So even from simple end vertex behavior and end edge behavior, which are governed by simple rules, you might get very complex system-wide behavior. One of the best examples of this is climate change. So you could represent climate change as a network where the vertices are different points on the globe and the edges are causality relationships between them. And we do understand all the basics of climate change. For instance, wind flows from high pressure to lower pressure, the rainfall happens when there is lower pressure, and so on and so forth. And yet weather is kind of hard to predict. And that's precisely because it's an example of an emergent phenomenon where even though you know the simple rules, you don't necessarily, you're not necessarily able to predict the emergent global behaviors when you put all of these tools together in a very large complex system. So these networks have a lot of structure in the sense that in many of these networks, you're able to reach one node from another in just a few hops. For instance, there is this well-known myth, actually almost a fact, known as 6 degrees of Kevin Bacon. In this case, if you draw the actor graph, if you use the Internet Movie Database, IMDb, and if you represent each actor or actress by a vertex in the graph, and an edge joining two actors, if those actors have acted together in at least one movie, then it can be shown that any actor can be reached from Kevin Bacon, the vertex representing Kevin Bacon, within 6 hops. So you can take just 6 jumps, or one over each edge, and reach any actor from Kevin Bacon. Milgram, a researcher at Stanford, did an experiment in the 1970s which showed that the human social network has just a few separates any pair of human beings with just a few edges. Typically, it's again known as 6 degrees of separation, where there are an expected number of 6 hops between any two individuals on the world, no matter how far or how unrelated they happen to be. And so, the actor network, the human network, and also other networks such as the World Wide Web, the human social networks that are in real online social networks such as Facebook, Twitter, and LinkedIn, peer-to-peer overlays, electric power grids, protein networks, a lot of these share this common characteristic where you can reach any node from any other node within just a few hops, just 6 hops or so. So why is this? We should be wondering why this is. And one of the common characteristics among all of these networks is that they've evolved naturally. It's not been the case that someone has come along and said, hey, here's how the network is going to be now and forever. Instead, these networks started small and then they evolved over time. All of these, whether it's a World Wide Web, whether it's a human social network, or whether it's an electric power grid, they evolved, whether it's evolution over a few years or over a few decades. In the case of Facebook, or in the case of the electric power grid, or as in the case of the human social network, evolution over many, many centuries and millennia. A lot of these are small world networks. Here I'm introducing a new term, a very interesting and very popular term called small world networks. We need to see what exactly they are. Before we see small world networks, let's see 2 important metrics that we can use to characterize networks. They are called clustering coefficient and path length. Let's do the path length first. The path length is something that you've already seen so far in our discussion. Path length essentially is, if you take any pair of vertices in the graph, you take the shortest path in between them, the shortest number of vertices you need to jump from one to reach the other. That's the path length of that vertex pair. You calculate this path length for every pair of vertices and you take the average among them. That's the path length of the entire graph, or the average path length in that graph or network. So the longer the path length is, the more spread out the network is in a sense, and the shorter the path length is, the more clustered the network is. But clustering is captured by a different metric known as the clustering coefficient, also abbreviated as CC. This defines something like the following. Given 3 vertices A, B, and C, if there is an edge between A and C, given an edge between A and C, and given an edge between C and B, that is A and B are common neighbors at C, what is the probability that A and B are also connected to each other? In other words, C has 2 friends, A and B. What is the probability that C's 2 friends are also friends of each other? That is the clustering coefficient. This is a probability, so it has values between 0 and 1. If the value is 0, then it means that essentially this is a very highly unclustered graph. For instance, tree networks have a clustering coefficient of 0. However, if it has a clustering coefficient of 1.0, the highest value possible, then it means that this is a highly clustered network. For instance, a complete graph where every vertex is joined to every other vertex is an example of a graph that has a 1.0 clustering coefficient. But different graphs lie at different points on the spectrum of clustering coefficient and path length. For instance, if you take the ring graph, a graph that you have seen when we discussed peer-to-peer systems and distributed hash tables before, you take the ring graph and you add a few successors and predecessors to each vertex, you get a graph that has a very high clustering coefficient, because if you have 2 neighbors, they're likely also to be neighbors of each other because they're likely to be successor and predecessor as well. But it has very long paths. If you have n vertices in your network, then the paths are on average order n in length. On the other hand, if you draw a random graph where the edges are added between random pairs of vertices, this can be shown to have a very low clustering coefficient, but it has very short paths. So the paths in between any pair of vertices are very short in general. So ideally, what we are used to in the human social network is high clustering coefficient, the fact that 2 of your friends are also very likely to know each other, but also very short paths, as we have discussed from Milgram's experiments and the 6 degrees of separation, that you can reach any other human being within just a few hops. That is what is characterized by the small world networks, which have a high clustering coefficient and short paths. So the reason I discussed the extended ring graph and the random graph is that you can actually show how to reach some types of small world networks by using these 2 types of graphs. Specifically, you take an extended ring graph, which has very structured edges, and you take one edge at a time and you make that edge point to random nodes. Okay, so you don't change the number of edges, but you take one edge at a time and make it point across random pairs of nodes. What happens as a result of doing that is that eventually, when you have changed all the edges over to being random, you get to a random graph, right? So you get from an extended ring graph to a random graph. And as a result, the clustering coefficient, which is very high for extended ring graphs, falls to be very low for random graphs. And the path length also, which is very high for extended ring graphs, also falls to be very low for random graphs. But they don't fall, these two things, the clustering coefficient and path length, don't fall at the same rate. In fact, the clustering coefficient falls much slower. It stays stable for much longer as you move from the ring graph to the random graph, while the path length falls very quickly. In other words, if you change just a few edges in your extended ring graph to be random edges, the path length falls very quickly because now a lot of the short paths will go via these random edges because they join very disparate portions of the graph. So you get these region of networks in between the ring graphs and the random graphs, which have a very high clustering coefficient, as high as the extended ring graphs, but have a very short path length, almost as low as the random graphs. And that is the region of small world networks. Once again, this is not all the small world networks that exist. This is one particular class of small world networks that exist. But essentially, this is a way of deriving small world networks which have this high clustering coefficient and short path length characteristic, as we are used to in the 6 degrees of separation and in the human social network. So small world networks are all around us. The network of actors is a small world network. The network of humans is a small world network. All online social networks such as Facebook, Twitter, LinkedIn are small world networks. Many of them have been shown by measurements to be small world networks. The co-authorship network, where vertices are researchers and edges between researchers, joint researchers who have co-authored at least one paper together, is an example of a small world network. In fact, there is a concept of an Erdos number, where the Erdos number is a number of hops between Paul Erdos, who was a very famous scientist, and you in the co-authorship network. The World Wide Web, the internet, all of these are examples of small world networks which have a very high clustering coefficient and yet have a very short path length. And many of these networks have grown incrementally, and in fact they can be modeled by using a preferential model of growth, where you add vertices sequentially or iteratively. When you add a vertex to a graph, you add some edges, and you add an edge from the new vertex to an existing vertex v with a probability proportional to the number of neighbors of v. So the number of neighbors that v already has is proportional to the probability with which v will be added to the newly added vertex. So if you use this rule, you can actually show that you end up with small world networks. So we've discussed small world networks. Let's change tack a little bit, and we'll come back to small world networks. Let's try and change tack a little bit and discuss degree. The degree of a given vertex in a graph or a network is essentially the number of immediate one-hop neighbors. So if a vertex has 3 edges, then its degree is 3. So the degree distribution in a network or a graph is the probability that a given node or a given vertex has k edges. There are different kinds of degree distributions. You can have a regular graph where all the nodes have exactly identical degrees, or a Gaussian distribution, or you could have a random graph with an exponential distribution where the probability that you as a vertex have k edges is e power minus k times c, where c is a constant, some constant. And of course you have a power law graph, which says that the probability that you have k edges incident on you as a vertex is proportional to k power minus alpha, where alpha is a constant. This is a very interesting distribution because when k is pretty small, like 1, 2, or 3, this probability is very high, but as k increases, this probability drops off very quickly. So there's a very large number of vertices that have very low degrees, but there are a few vertices that have very high degrees as well. So how do you represent this? Well, this can be represented by what is known as the log-log plot. This is a very well-known plot. Here you represent the node degree on the x-axis. Instead, what you plot is the logarithm of the node degree. So you notice that the values of node degree go exponentially up, 1, 10, 100, and 1000 rather than 1, 10, 20, and 30. And on the y-axis, you plot the number of nodes that actually have that node degree. So for instance, if the point is x-axis equals 1 and y-axis equals 1 million, it means 1 million vertices in this graph each have a degree of 1. Okay, so you plot this distribution function. Once again, the y-axis is also logarithmic, as you notice here. It goes from 1, 100, 10,000, and 1 million. And the power law graph, if you plot the degree distribution for a power law graph, it's going to be a straight downward sloping line, as shown by this green line over here. Okay, so a very large number of vertices have very small degrees, as in the top left portion of the curve, but some vertices also have a very high degree, and these are the high degree vertices that are present in any power law graph. The exponential graph is not a straight downward sloping line. It's curved at its head, the top left portion of the plot, and it's also curved at its tail, the bottom right portion of the plot. There are also some distributions which are heavy tail distributions, which are straight downward sloping at their tail, the bottom right portion, but they are not necessarily heavy headed, which is top left portion. Okay, so they are almost like power law graphs in the sense that they have some vertices that have a very high degree, but they don't have that many vertices with a low enough degree as a power law graph. So this log-log plot is the best way for you to distinguish when a particular graph or when a particular network is either power law or heavy tail or exponential or something else. You draw the log-log plot. If it's a straight downward sloping line, it's a power law graph. If it has a heavy tail, if it has a straight tail, then it's heavy tailed, and otherwise it's some other distribution. So a lot of small world networks are also power law graphs. For instance, the internet backbone graph, the telephone call graph, protein networks. The World Wide Web graph is in fact a small world graph, and also a power law graph that has a value of alpha equals somewhere between 2.1 and 2.4. Remember that you have in a power law graph a degree of k with probability proportional to k power minus alpha. The Gnutella peer-to-peer system has a heavy tail degree distribution. It's not necessarily power law, but it is heavy tail, so it has a straight downward sloping tail in the log-log plot. Power law networks are often called as scale-free networks. For instance, in Gnutella, you have about 3.4 edges per vertex, independent of the number of vertices that are present in your network or in your graph. But then not all small world networks are power law graphs, and vice versa. For instance, co-authorship networks are small world, but they're not necessarily power law. And also not all power law graphs are small world. You can generate power law networks using the degree distribution where you have disconnected components of the graph where vertices are not necessarily reachable from each other, and so the graph is not a small world network. But many small world networks are in fact power law graphs as far as you find them in reality. And because a lot of these graphs are small world and power law, their resilience comes into the question. Most nodes have a small degree in these graphs, but a few nodes have a very high degree in these graphs. So if you launch an attack on one of these graphs, if the attack is random, for instance, you kill a very large number of randomly chosen nodes, this will not disconnect the graph. Okay, this is why attacking a power law small world graph randomly is not very effective at all. But if you target some of these very high degree nodes in the power law small world graph, this has a much higher chance of disconnecting the graph. Okay? And this is essentially why in the human body, for instance, because the graph of proteins in the human body or chemicals in the human body is a small world network and also a power law network, a few of the nutrients are very high degree nodes in the graph. So essentially edges in this protein graph are edges that join two chemicals that react with each other, and so some nutrients happen to be have a much higher degree than other nutrients because they react with a lot of other chemicals in the body. And these nutrients are essentially the vitamins in the human body, the minerals that the human body requires, like calcium and potassium. So if you have a shortage of any of these vitamins or nutrients in your body or minerals, you're likely to be in trouble. But if you have a shortage of some of these other random chemicals that are there in your human body, then it's not likely that you're going to be affected all that much. Similarly, networks like the internet as well as the electric power grid, if you target a few high degree vertices, that's much more likely to disconnect the graph and cause a partition and cause outages in the network. But if you target randomly chosen vertices, and that's not likely to have any effect on the network itself. What about routing in these networks such as the internet? If you build shortest path routes between every pair of vertices, it turns out that in small world power law networks, most of these shortest path routes will pass through some high degree vertices in the graphs. So these high degree vertices get highly overloaded with these shortest paths, and they're likely to suffer congestions and perhaps in fact even crash. And as we have seen from the previous slide, if you disconnect some of these high degree vertices, it's also likely that the entire graph will be disconnected and you might have an outage in the network. So this should tell you why there are these frequent outages in networks such as the internet, in networks such as the electric power grid. It's because these high degree vertices suffer congestion and they might crash as a result of that, and because when they do, they disconnect large portions of the graph and you end up having an outage. So in the internet, one of the solutions to this is to add some amount of randomness in the path selection. You don't always prefer the shortest path, but you take some hops in your path that are random hops, and this avoids going through the high degree vertices with some probability, and so the load on the high degree vertices reduces, they're less congested, and they have a lower chance of crashing. To wrap up our discussion of structure of networks, networks are all around us, both man-made networks such as the internet, the World Wide Web, and peer-to-peer networks, as well as natural networks that have evolved over centuries and millennia, such as protein networks and the human social network. Yet a lot of these networks have common characteristics. Many of them are small world networks that have a very high clustering coefficient and very short path lengths. And they're also power law, where you have a very large number of vertices that have a small degree, but some vertices have very high degrees. And it's useful to know these characteristics because when you design distributed systems and distributed protocols that run over networks like the internet, that run over, that deal with social networks such as the online social networks, it's useful to know these characteristics so that you know exactly how your protocol is going to behave on these when it sends packets, when it sends messages over these networks, or when you run a graph processing algorithm that is dealing with such power law graphs. So you can better predict how your distributed system is going to behave when it runs over such networks, small world networks, such as the internet.